June 7, 1944, 2:15 p.m., Benneville, France. A 60-foot steel bridge slides across the Caen Canal while German artillery shells scream overhead. British Royal Engineers duck behind panels, hammers still swinging. Their commanding officer checks his watch. 40 men, 4 hours of construction, 0 cranes, 0 welding equipment, just pins, panels, and pure desperation. But here's what makes this moment extraordinary. This bridge shouldn't exist. The technology to build it didn't exist 4 years earlier. Military doctrine said constructing bridges under enemy fire was suicide. Every military textbook of the 1930s declared it impossible. Yet by the end of World War II, Allied engineers would build over 3,000 of these bridges, totaling 55 miles of roadway across rivers, valleys, and bomb craters. Field Marshal Bernard Montgomery would later declare, "Without the Bailey Bridge, we should not have won the war." This is the story of how one civil servant sketched a design on the back of an envelope and created the most important piece of military equipment you've never heard of. A bridge so simple that factory workers with 0 engineering experience could build the parts, so portable that 4 men could carry each section, so strong it could hold a 40-ton tank, and so fast to assemble that combat engineers could throw it across rivers while bullets tore through the air around them. The Bailey Bridge didn't just change how armies crossed water, it changed how wars were won.
To understand why the Bailey Bridge was revolutionary, we need to go back to 1939 and a problem that was keeping British generals awake at night. The British Army had a bridge. It was called the Inglis Bridge, inherited from World War I, and it had one catastrophic flaw. It could only carry 19 tons. That sounds reasonable until you learn that Britain's new Matilda tank weighed 23 tons. The Churchill tank, still in development, would weigh 40 tons. Every modern military vehicle was too heavy for the standard military bridge to carry. But the problem went deeper than weight capacity. Existing bridges required massive cranes to lift pre-assembled sections into place. They took days to construct. Their components were heavy, specialized, and could only be built by experienced steel fabricators. When retreating armies destroyed bridges, advancing forces faced a brutal choice: find another route or wait days for engineers to build a replacement while the enemy escaped. In 1940, as Nazi Germany demonstrated the devastating effectiveness of rapid armored warfare, this became an existential problem. Blitzkrieg worked because German forces moved fast. If British and American armies couldn't keep pace, they couldn't win. The British War Office issued a specification that seemed impossible to fulfill. They needed a bridge that could be assembled by regular soldiers using only hand tools. Every component had to be light enough for men to carry without machinery. The parts had to be mass-produced by factories with no specialized experience. Most critically, it needed to be strong enough to carry a 40-ton tank across a 200-foot gap. Engineers called it a fantasy. One prominent military contractor told the War Office, "What you're asking for violates the laws of physics." But there was one man who disagreed. A quiet, unassuming civil servant named Donald Coleman Bailey, and he had an idea he'd been thinking about for years.
Donald Bailey was born September 15, 1901, in Rotherham, Yorkshire. He studied civil engineering at Sheffield University and spent years working on reservoir construction. By the late 1930s, he was working for the Experimental Bridging Establishment, a small government research organization with a tiny budget and an impossible mission: modernize Britain's obsolete military bridging equipment. Bailey was not a typical engineer. While his colleagues designed elaborate bridge systems using advanced materials and complex assembly methods, Bailey approached the problem differently. He asked himself, what if, instead of making the bridge more sophisticated, we made it simpler? The breakthrough moment came in 1940. According to witnesses, Bailey was being driven to a meeting of Royal Engineers when he pulled out an envelope and started sketching. By the time the car arrived, he had drawn the fundamental concept that would change military engineering forever. His idea was deceptively simple: build the bridge like a child's construction toy. Bailey proposed creating standardized panels, each exactly 10 feet long and 5 feet high, made from welded steel in a cross-braced rectangular pattern. These panels would have holes at each corner. Engineers would connect the panels side by side using simple steel pins hammered into the holes, building the bridge's supporting walls. Wooden planks laid across steel transoms would create the roadbed. The genius wasn't in any single innovation, it was in the system. Every component was interchangeable, every piece simple enough to mass produce, every part light enough for 4 to 6 men to carry. And most critically, the bridge could be strengthened simply by adding more panels, stacking them horizontally or vertically, depending on the load requirements. The War Office was skeptical. One official told Bailey, "It looks like something from a toy shop, not a battlefield." But Bailey had calculated the load-bearing capacity down to the last rivet. On February 14, 1941, the Ministry of Supply gave Bailey an ultimatum: build a full-scale working prototype by May 1st, or the project would be canceled. Bailey had less than 3 months to prove his envelope sketch could become reality. What happened next stunned everyone. Bailey assembled a team, including bridge designer Ralph Freeman, who had engineered the Sydney Harbour Bridge in Australia. Working around the clock at the testing facility in Christchurch, Dorset, they fabricated the first full-scale panels and built a test bridge across a field. Now came the stress test. Engineers drove a World War I Mark V tank onto the bridge and parked it in the middle of the span. Weight-bearing jacks underneath were removed. The bridge held. They loaded smaller tanks onto a platform built on top of the Mark V. The bridge still held. Finally, they filled the Mark V with scrap iron until it weighed far more than any modern tank. The bridge didn't budge. But the real breakthrough came when they calculated the numbers. By stacking panels too high and too wide, a Bailey bridge could carry 75 tons across a 100-foot gap. Triple the panels, and it could support even heavier loads across longer distances. And because each panel weighed just 570 pounds, 4 to 6 men could lift and position it without machinery. And most critically, the bridge could be strengthened simply by adding more panels, stacking them horizontally or vertically, depending on the load requirements. In July 1941, full production began. By December 1941, the first Bailey bridges entered military service. Within months, over 650 British firms, including the Littlewoods department store chain, were manufacturing bridge components. Production eventually reached 25,000 panels per month. The man who had been told his design looked like a toy had just created one of the most important weapons of World War II. And he'd done it with a sketch on an envelope and faith in simplicity.
The first operational Bailey Bridge went up on the night of November 26, 1942, over the Medjerda River near Medjez El Bab in Tunisia, built by the 237th Field Company of the Royal Engineers. But the first Bailey Bridge built under direct enemy fire came in Sicily, at a town called Leonforte, constructed by members of the 3rd Field Company, Royal Canadian Engineers. German forces held the high ground. Machine gun fire raked the construction site. Mortar shells exploded across the riverbank, and yet the engineers kept building. This became the pattern repeated hundreds of times across North Africa, Sicily,
Italy, and eventually Western Europe. As German forces retreated, they systematically destroyed every bridge, mined every road, and turned every river crossing into a killing zone. The Wehrmacht's strategy was simple. If we can't stop them on the battlefield, we'll stop them at every river. But they hadn't counted on the Bailey Bridge and the engineers willing to build it under fire. Edmund McNeill, a warrant officer with the 284th Engineer Combat Battalion, 9th Infantry Division, described the reality of Bailey Bridge construction under combat conditions. His words paint a picture far removed from the clean engineering diagrams. When you're building the thing, the Germans are throwing mortar shells on top of you all the time. It wasn't a smooth operation. There was always a problem. Especially when a plane came over and dropped a bomb on the damn thing, right when we were halfway through building it. Or they'd machine gun us, or we'd run into mines. The construction process required brutal efficiency. Engineers would arrive at a destroyed bridge site, often still under German observation. While infantry units provided covering fire, bulldozers cleared approaches to the riverbank. Engineers laid out rollers, metal tracks upon which the bridge sections would be pushed forward across the gap. The assembly began with the launching nose, a lighter angled section that would extend out over the water or gap. Behind it, crews assembled the first full section, 2 vertical panels on each side, connected by transoms, the horizontal beams running across the width. Stringers, smaller beams running lengthwise, were laid across the transoms. Finally, wooden chesses, planks 12 feet long, were placed across the stringers to form the actual road surface. 1 section complete. 9 more to go for a 100-foot bridge. And the Germans are still shooting. McNeill continued. All you'd hear, beyond the hammering, were the sergeants, "Get that, wham that, hit that. Don't you know how to hit that?" The sledgehammers would be going like crazy. You're slamming pins in all over the place. You didn't have to tighten up any bolts or anything. You just bang them all in there. But the real danger came from the relentless precision required. You always wore your helmet, always, because if you fell, you were falling on steel. A man would fall overboard. We'd get him and pull him up, and he'd have a bullet hole in him. That happened. German machine guns would wipe out 4 or 5 guys standing on the bridge. The engineers developed brutal pragmatism. Work never stopped for casualties. Men would step over their wounded comrades to continue hammering pins. If a section was destroyed, they'd rebuild it immediately. Speed wasn't just about military advantage. It was about survival. The faster you finished, the sooner you stopped being a target. Some bridges took 3 to 4 hours under ideal conditions with 40 men. Others took 2 days under heavy fire. The record for an 80-foot Bailey Bridge was set by the 1st Canadian Division Engineers, 1 hour and 8 minutes from first panel to trafficking tanks.
June 6, 1944. As Allied troops stormed the beaches of Normandy, Royal Engineers were already preparing for the next phase. Getting off the beach was only the beginning. To push inland, armies needed to cross the Caen Canal, the Orne River, and dozens of smaller waterways crisscrossing the French countryside. German forces had prepared for this. Every bridge had demolition charges. Every river crossing had observation posts crawling in artillery fire. The Normandy bocage, with its dense hedgerows and sunken lanes, turned every 100 yards into a potential killing ground. In the pre-dawn hours of June 6th, British paratroopers had conducted a daring glider assault to capture intact 2 bridges, Pegasus Bridge over the Caen Canal and Horsa Bridge over the Orne River. Led by Major John Howard, the assault succeeded. But these bridges alone weren't enough. The entire Allied advance depended on rapid bridge construction to get armor and supplies flowing inland. The first Bailey Bridge, built in France, went up on June 7-8, 1944, just 500 meters south of Pegasus Bridge, near the Château de Benneville. British engineers of the 249th Field Company worked through the afternoon and into the night, finishing at 2:15 p.m. on June 8th.
This 60-foot span across the Caen Canal became the template for hundreds more. The bridge consisted of 4 standard Bailey sections, assembled under German artillery fire. But it worked. Within hours, British armor was rolling across, pushing deeper into Normandy. The Bailey Bridge's modular design proved perfect for Normandy's challenge. German forces had destroyed most bridges, but often left the stone or concrete piers intact. British and American engineers could quickly measure the gap, calculate the required panels, truck in the components, and build a crossing in a fraction of the time traditional bridging would require. What made the Bailey revolutionary wasn't just construction speed, it was adaptability. Need to double the bridge's strength? Add more panels horizontally. Need to span a longer gap? Stack panels vertically and add more sections. A bridge that could carry light vehicles could be strengthened overnight to carry tanks simply by bolting on additional panels. By late June 1944, the U.S. Third Army alone had employed nearly 27,000 feet of Bailey bridges of varying lengths across France. As Allied forces pushed toward Germany, the bridges kept pace, thrown across the rivers of Belgium, the Netherlands, and finally, the Rhine itself. In March 1945, as Allied forces prepared to cross the Rhine, the final barrier between them and Germany's heartland, Canadian engineers built Blackfriars Bridge at Ries, Germany. At 1,814 feet, including approach ramps, it was the longest Bailey bridge ever constructed during the war. It carried thousands of tanks, trucks, and men into the final campaigns of the European War.
The success of the Bailey Bridge came at a terrible price, paid by the engineers who built them. Combat engineer casualties were among the highest of any non-infantry specialty. Bridge sites were natural choke points, always within range of German artillery. Engineers building bridges under fire had no cover, no concealment, and no way to fight back, while their hands were full of steel panels and hammers. Edmund McNeill remembered the toll. Guys would jam their fingers, break their hands, break their arms. If you fell down, you'd most likely crack all the teeth in your mouth. And you always wore your helmet, always, because if you fell, you were falling on steel. But the physical danger wasn't the only challenge. The mental strain of working under fire, knowing each hammer blow might be your last, broke some men. Others developed a fatalistic attitude. Once we got a bridge done and we were across and moving forward, we wanted nothing to do with that bridge again. Nothing, McNeill said. That is, until they were assigned to build the next one. The production side had its only challenges. British quality control was extraordinarily strict because lives depended on interchangeability. If a panel manufactured in Birmingham didn't fit perfectly with transoms made in Coventry, soldiers would die trying to make it work under fire. Over 650 firms across the UK manufactured Bailey components, each operating under rigid specifications to ensure every piece from every factory was identical. The Americans initially struggled with this. In 1944, the U.S. 31st Engineering Regiment discovered that several hundred American-made Bailey panels were either slightly too large or too small. The problem was traced to fabrication gauges, whose precision had been ruined by poor handling. Some 850 American-built Bailey kits had to be tracked down and marked as standalone types, never to be mixed with British or properly manufactured American components. It was an embarrassing reminder that precision engineering tolerances mattered as much as combat courage. Yet despite these challenges, the Bailey Bridge worked. And it worked so well that Field Marshal Bernard Montgomery, commander of British forces in Northwest Europe, issued a remarkable statement in 1947. Bailey bridging made an immense contribution toward ending World War II. As far as my own operations were concerned, with the 8th Army in Italy and with the 21st Army Group in Northwest Europe, I could never have maintained the speed and tempo of forward movement without large supplies of Bailey bridging. Without the Bailey Bridge, we should not have won the war. It was the best thing in that line that we ever had.
This wasn't military hyperbole. Montgomery was stating a tactical fact. The Allied strategy in 1944 to 45 depended on maintaining momentum, on pushing German forces faster than they could establish new defensive lines. Every destroyed bridge was an opportunity for the Wehrmacht to reorganize. Every river crossing delayed was another day for Germany to reinforce defenses. The Bailey Bridge eliminated those opportunities. When Germans destroyed bridges, Allied engineers rebuilt them in hours, not days. The advance never stopped. General Dwight D. Eisenhower, Supreme Allied Commander, echoed Montgomery's assessment, calling the Bailey Bridge one of the three most important technological developments of the war, alongside radar and the atomic bomb. That might seem like an overstatement until you consider the alternative. Without rapid bridge construction, the Allied advance from Normandy to Berlin would have taken months longer. The war in Europe might have extended into 1946 with incalculable costs in lives and suffering. Donald Bailey, the quiet civil servant who sketched a design on an envelope, was knighted in 1946. He received £12,000 from the British government, a modest sum for a man who had helped win a world war. Bailey lived until 1985, long enough to see his bridge become the global standard for rapid bridge construction in military and civilian applications worldwide.
The story of the Bailey Bridge didn't end in 1945. If anything, the post-war decades proved that Donald Bailey had created something even more valuable than a military weapon. He had invented a universal solution to a fundamental human problem: how to cross gaps quickly, safely, and economically. In the immediate aftermath of World War II, Bailey bridges went to work rebuilding war-torn Europe. Cities with destroyed infrastructure used Bailey components to restore river crossings while permanent bridges were reconstructed. The design's modularity meant bridges could be customized to any span, any load requirement, any environmental condition. Perhaps the most dramatic civilian use came in 1975, when the Tasman Bridge in Hobart, Tasmania, was destroyed when a cargo ship struck one of its piers. Within weeks, Australian engineers had assembled a 2,585-foot Bailey Bridge, the longest ever built, to reconnect the two halves of the city. The temporary Bailey remained in service until 1977, when the permanent bridge reconstruction was complete. For 2 years, an entire city depended on a design created for battlefield conditions. Modern armies still use Bailey-type bridges. The design has been updated, components refined, materials improved, but the fundamental concept remains unchanged. When disasters strike, from earthquakes to floods, Bailey bridges remain the first response. They can be transported by truck, helicopter, or even airdropped. Assembly requires minimal training and no specialized equipment. A Bailey bridge can be operational in hours, not days or weeks. India has become one of the world's largest users of Bailey bridges, employing them extensively in the Himalayan regions where mountainous terrain and monsoon conditions regularly destroy permanent bridges. The Indian Army's Madras Engineer Group has set modern records for Bailey Bridge construction, including a 190-foot span assembled in record time following devastating landslides in Wayanad, Kerala in 2024. The core principles that made the Bailey revolutionary in 1944 remain relevant in 2025. Simplicity, modularity, portability, and strength. In an era of increasingly complex technology, the Bailey Bridge stands as proof that sometimes the best solution is the simplest one.
On June 7, 1944, 40 British engineers assembled a 60-foot bridge across the Caen Canal while German artillery pounded their position. 4 hours of hammering, 570-pound panels lifted by hand, simple pins connecting modular sections into a structure that could carry 40-ton tanks. That bridge and the 3,000 others like it built across Europe didn't just change how armies crossed rivers. They changed how wars were won. They proved that sometimes the greatest innovations come not from complexity,
but from radical simplicity. That the best solutions to impossible problems often start with a sketch on an envelope and faith that good engineering requires nothing more than good thinking. Donald Bailey never wanted fame. He never sought glory. He was a civil servant who liked bridges and believed that water obstacles shouldn't stop advancing armies. He created something so effective, so fundamentally well-designed, that 80 years later, his bridge is still being built, still saving lives, still connecting communities divided by nature or disaster. The next time you cross a river, think about the engineers who once built bridges under fire. Think about the men who carried 570-pound panels while bullets flew past their heads. Think about the quiet civil servant from Yorkshire who changed the course of history with nothing more than steel, pins, and an envelope sketch. Because the Bailey Bridge isn't just a piece of military history. It's proof that when you solve problems simply, elegantly, and well, your solution can outlast armies, outlive empires, and continue making the impossible possible for generations to come. If you enjoyed discovering the engineering brilliance behind the Bailey Bridge, subscribe for more stories about the technical problem solvers who changed history. Hit that notification bell so you never miss our deep dives into military engineering innovations that won wars through ingenuity, not firepower. Next time, we'll explore how Allied codebreakers used mechanical computing to crack the German Lorenz cipher, a code so complex that even its operators couldn't explain how it worked. It's a story of mathematical genius, captured equipment, and the birth of modern computing, all in a race against time to read Hitler's most secret communications.